Okay, in this video, I'm going to be talking about I sequences and D sequences, which are not exactly super relevant for VR, but it's stuff related to Slice, which you should probably know. Um, it's also useful, like, not exactly for a problem relating to Slice. I mean, it's inserting Slice, but also you can kind of use this to simplify your solution if you get something like if you have already a solution, you can get something shorter. So this was a theory developed by, well, the theory related to this was developed by Sebastiano Toronto, and I'm going to link his page about this. I'm just going to be talking about basic stuff here. So definitely read his page for more. So what I'm going to do in this video is I'm going to define I sequences and D sequences. I'm going to tell you how to recognize them, in particular how to tell them apart. And then I'm going to be proving my claims, basically. I'm going to be proving that this actually works. So let's define I sequences. And I'm going to define a slightly different way from him, but this is a bit cleaner, I believe. So an I sequence is going to be something that commutes with anything that commutes with E. And by the way, I'm going to be assuming that all of our sequences are in the DRUT, so I'm going to be assuming anything is in this moveset. Unless I make some specific examples that you beyond this moveset. Yeah. A D sequence, I'm going to be defining as anything that commutes with E2. And that does not commute with D. So let's make some examples. So obviously the empty sequence, and obviously anything that simplifies to empty sequences. But also, this is a nice sequence. Why? Well, because U2 are irrelevant for the E-slice. So we can just ignore any U2s when assessing whether a sequence is an I or D sequence, or I guess even R2U, R2. They need to go that way. So yeah, basically this is as if it was R2, R2, which does nothing. So R2, in particular, you can take a cube, do R2, R2, and notice that it does literally nothing to the slice. And there are more examples like R2, F2, B2, R2. And yeah, you can kind of play around with these. These sequences examples include R2L2, R2F2, R2. And like these are really the only ones you need to know. Yeah. So what are these useful for? So the way Sebastiano approaches the slice is a little bit different from me. So the way I did it was I had a skeleton that does not solve the slice, and I wanted to insert E moves to solve the slice in the optimal way. And my skeleton was already simplified. What he does is he considers solutions. So basically, they're already solutions, they already solve the slice, but they're suboptimal. And he tries to see whether you can insert E moves, E moves, E2, E prime, whatever, to reduce the move count, while also still providing a solution. And he doesn't actually solve this entirely. He kind of gives some results on how when you can insert 2 slices or 3 slices, whereas like VR is more complete, like it's airtight pretty much. The only thing VR is not good for is when the slice is solved by inserting a full algorithm. But like that's easy to do anyways. So yeah, I sequencing and D sequences. Let's just give an example of when I sequences can be useful. So just a basic example. So let's say you have something like this within your final solution of an FMC solve. And well, actually this can be simplified because you can insert an E prime here and E here. And the idea is that because R2 is an I sequence, it commutes with E. So if you consider this new thing where you have the E prime and the E inserted here, the E can be commuted past the R2 and it simplifies with the E prime. So this is still the same. But if you write it like this, then this actually cancels 2 moves, and this, well, this is adding 0 moves. So basically, we obtain the result that this thing is the same thing as Y, and then R2 Uy prime. So this is the basic example of how to use this. This is like the 2 insertions. And if you have E2s, you can also have this being a D sequence. Otherwise, it doesn't quite work. There are more examples. You can kind of play around with I sequences, D sequences, like surrounding them with E prime, E2, whatever insertions. And you can read again. You can read Sebastiano's page how to deal with 3 insertions. So what I'm going to do now is I'm going to be giving you a systematic way to test whether a sequence is an I or D sequence. So the first thing that we're going to do is we're going to, well, first of all, you get rid of all of the U and D moves, as I told you before. So there's no need to consider them. So let me actually give an example. R2. Let's do that. Okay. So this is how to tell whether a sequence is I, D, or none of them. So we start reading the sequence left to right, and we start with the first move. This is an R2. So now we scan the sequence until we meet something that is either an R2 or an L2, and in particular because L2 is opposite of R2. So we go there and we go here. Okay. And now this is either an I or D sequence, and we successfully broken off a piece from the sequence, and we can now treat the remaining in the same way. So in this case, we have F2, and we need to find either an F2 or a B2. Here we find the first thing we find here is a B2, and then here. All right. Now, what you're gonna do is you want to. So in this case, we did meet an L2 at the end. Let's say we had an example something like this. Okay, we have R2, we get L2. Here F2. Well, we never meet a B2 here. So in this case, our procedure is kind of suspended. And when you get something like this, it means that you do not have an I or a D sequence. So this is neither of them, because of this F2 R2 at the end. So just the fact that it closed means it's either an I or a D sequence, and you just have to figure out which of them it is. So now you consider each subsequence. I guess we can call this like primitive subsequences, and you have to check whether these are I or D sequences. So there is a simple rule for this. So let me just draw your table. So there are 2 things you need to check. You need to check whether the moves at the extrema are the same or opposite. So for example, actually in all these cases they're opposite, because R2 L2, F2 B2, R2 L2. But you can theoretically have something like this, which you have boom and boom, and these are the same, so this will be the same. The second thing you need to check is how many moves are in particular the parity. Obviously you can include this because there are 2, but you can just count the ones in the middle. So they can be even or odd. So in this case there is an even number because there's only F2, here is odd, R2 L2, here is an even because that's that is R2 L2. This is even because it's 0. This is odd, odd, even. And the rule is very simple. This is the rule. And so let's apply this to our 2 examples, I guess, because it's neither. It's no point. I guess this is the I sequence, but yeah. So this is an I sequence. So you have opposite and even, so that's a D sequence. And this is opposite and even, so that's a D sequence. And you can do the same thing here. This is same and odd, so that's D. Opposite, even, that's D. And then you basically want to kind of add these together. And the rule is that I plus I equals I, d plus d equals I plus d equals d. This is basically the same as arithmetic mod 2. So in this case, we get this is an I sequence and this is an I sequence. Kind of happen to pick two I sequences, but yeah. Yeah, so this is how you do this, and this is also useful. So this kind of thing where you insert it in E prime, whatever, this can also be useful to simplify the slice outside the DR slice. So even if you did DR on UD, you can do this for other stuff to simplify the leaf slice, for example, like the HDR to leaf slice part, or maybe you inserted to ETLG, but you didn't really pay attention completely, and there's still slices you can insert. Yeah, basically, it's a good idea when you have your final solution to just scan for like parallel moves and see if there's anything you can do. Yeah, for example, I'll just give an example. One time I had this, and then I had and then continue and then continue. I had this part in my sequence because I was careless in inserting some. Actually, I think it canceled before, but yeah, whatever. I think the U2 canceled at the very least. So yeah, I had something like this because I wasn't very careful in the end. But you can fix your mistake if you got something like this because here you have LR2 and you okay. So basically, we know that we want to insert M moves, probably an M2. Because outside the slice, it's unlikely trying to insert an M or M prime. And then you see, okay, you have F2, U2, U2, F2. Okay, this is just the R obviously is ignore. And then you have R2, so it kind of stops here. So actually, we can insert an M2 here and M2 here, because this is an I sequence. It doesn't even matter; it's an I sequence. Even if it had been a D sequence, that would have been fine. So basically, we can insert M2 here and M2 here, and we're reduced by one move. So if you have a solution, you can sometimes get a shorter solution by doing this. Right, let's prove our results. Yeah, okay. So the first thing that we want to do is to, I guess, the part for noobs is over. Now we're theory maxing. Yeah. So an E move, if you look at it from the top, is this permutation here, okay? And one thing you can try to do is determining what is the centralizer of an E. How many permutations are there that commuted this? And okay, you might correctly guess that it's just the powers of this fourth cycle. Let's prove it by group theory. So the centralizer of an element, the order of centralizer of an element is given by the order of an entire group divided by the size of the conjugacy class. And okay, this is 4 factorial. And what is this? Well, the number of n cycles is n minus 1 factorial. So that's 3 factorial. So this is actually 4. Which, and in particular, so the size of the conjugacy class contains as kind of 4, and it contains all the powers of the cycle. So it's actually this set must like it must be that identified correctly that all the in an element commutes with the if and only if it's a cycle on the things. Let's just do the same with E2. So E2 is something like this. It's a 2-2 swap. Oh my gosh. Hold up. Okay. And okay, so S4 divided by size conjugacy. And in particular, we have that E2 must contain the conjugacy class of E2 must contain the centralizer of E2 must contain the centralizer of E. So again, this is 4 factorial. And how many of these are there? Well, it's how many ways are there to divide this into 2-2 swaps? And the answer is actually 3. Look, usually there are 3 elements. This is the VR playlist, for frick's sake. Like you should know that. So this is 8. Right, in particular, we know that the centralizer of E is a subgroup of the centralizer of E2. Actually, it's a normal subgroup. Because its index is exactly equal to 2. And we know that when When two groups are contained one within the other within index up to, then actually the smaller one is the normal subgroup of the bigger one. So we can also try to analyze the group structure of this, and actually the centralizer of E2, so which is basically I in D sequences, is actually isomorphic to the dihedral group on the square. So that's a group of order 8. Okay, that's not hard to convince yourself of because it contains the rotations. Like if just from seeing just from representing E as this permutation here, you can see that this is a rotation and the powers are just rotations. And then okay, E2 is that, but like you can consider, for example, this one. This is the flip, so it contains the flip as well. So yeah, you can very easily see how this isomorphism works. And the centralizer of E is basically corresponds to well, the rotation group, which is Z mod 4Z. Right. So the first thing that we're going to prove now is, well, I guess this kind of silly addition rule. That's not hard. That's due to the fact that D4 mod Z mod 4Z is isomorphic to Z mod 2Z. I mean, it's a group reward to what else do you want? So like that's immediately done. This is basically saying that if you take a symmetry of the square and you flip it twice, then it's as if you just do a rotation. And if you do a rotation and it's something that flips, then you basically flipped it. It's about like what side of the square ends up on top, basically. You can think of it this way. Right. Now, what I'm going to prove is that this algorithm works. So the first thing I want to do is to prove you that if you have F2 and then something that doesn't, so basically there's no more B2 at the end, so R2, L2, L2, R2, whatever, something that contains only R2 and L2, that this will never be an I or D sequence. Okay, so actually that's not very difficult. You can just take this modulo Fio group. Because actually, S4 contains D4. Like that, there's no error actually. I mean, I guess that's an inclusion like this. And D4 contains, it does contain Z mod 4Z, but it also contains the Fio group. The Fio group is actually a subgroup of D4, as you can check very easily from yourself. So actually, modding by V is modding by a subgroup of D4. So if this is not 0, then our that will not work. Or like if it's not 0, okay. I guess I should really compute D4 mod V, and D4 mod V just happens to be R2, F2, R2, which is just this diagonal swap. Okay, so basically we just need to check that this is not equal to 0 or to a single diagonal swap. And I guess I should write it like this, really. So, okay, if you do modulo V, then you basically, okay, what are the possible answers? So modulo V, there's no difference between R2 and L2. So we only have two possible things we can have, either F2 or F2R2. This is a 2 swap, but it's an adjacent 2 swap. And this is a cycle, so QED. So, okay, so we've proven that if the last segment doesn't end at the like as we intended to be, then we don't get an I or D sequence. I think it's pretty obvious at this point to see that this procedure does actually break up any sequence into I, D sequence, and some procedural, I guess. So the only thing that's left for us to prove is this rule here. And we don't really want to use this, this V, mod V anymore. What we can do, well, we use the fact that R2L2 is a D sequence, and that R2F2 R2 is a D sequence. I know I wrote them differently. And I guess technically also using the fact that F2B2 is a D sequence, and that all possible corner swaps basically F2 R2 F2 L2 B2 L2, all of these ones. Yeah, they're rotating versions, flipped versions, or whatever. So I don't think it should be hard for you to believe that. All right, so if you have, so let's say we have R2 and we have an even number of F2 B2s, right? Of F2s and B2s. So first of all, because we're only working with F2s and B2, we can simplify them, okay? Because obviously F2s and B2s commute. So basically, we can assume that we are left with either F2 B2 or so let's do like the R2 part. All right. Or actually, we don't even need to do that because basically what I'm gonna do is even without simplifying. That's actually very simple. So let's say you have like R2, F2, B2, F2, B2, whatever. What I'm gonna be doing is I'm gonna be inserting R2, R2 here, kind of artificially. And what this does is that it breaks this up into more I sequences and whatever, into like more elementary sequences. And notice that this is a corner swap, so this is a D sequence. This is a corner swap, this is a D sequence, this is a D sequence. And basically, you're going to end up, at the end, we're going to have like, let's say we end up with L2, I don't know. We're going to end up with another R2, R2, and we're going to end up with like this thing here. So basically, we see that we get a +1 for each move that we have in the middle, and we get a +1 if these two moves are opposite, because R2, L2 is a D sequence and R2, R2 is not. So that's QED. That just proves the result. So the way I wanted to show you about this, first of all, is because it's just useful knowledge to have for solving the slice, or like really for reference C, once used, especially if you use DR. This will come up very often. The second reason is because I have an experimental method to not turn the cube while using VR, find the slice without turning the cube. I say without turning and not without touching, because there's technically cube rotations involved. It's an experimental method. I actually don't think it's worth it. I just want to put the idea out there. There's also some cool math there, so that's kind of why I want to do that. So I guess see you in the next one.